Hello. Bathroom gayeti क्या साउथ की बात में जो छात्र में वहाँ है देखो जानी जानी पानी थोड़ा ठंडा पानी तो बात चल मैं ये तो ला देती हूँ चल ले ले तू ले ले दे मैं उठता शायद नवाब साहब नवाब साहब नवाब साहब नहीं उठता नवाब साहब चाय लाई हूँ मैं आपके लिए जल्दी आइए आप
Hello students, good morning. How are you? Hope all are doing well planned strategic revision for this re-exam. Come on, today our chapter is rotational mechanics. This chapter contributes 2 to 3 questions in NEET. And this chapter, you need to focus on formulae, concepts, numericals. And in this chapter, if you compare this chapter with linear motion, if you compare this chapter with linear motion, then it will be easy for you. See, linear motion, linear displacement formula u plus v by 2 into t, which is equal to ut plus half ad square. Here u and v are initial and final instantaneous velocities. And here this a is acceleration, t is time. Its corresponding formula in rotational motion is angular displacement, theta. Angular displacement also in a similar manner can be written as initial angular velocity plus final angular velocity by 2 into t, which is also equal to initial angular velocity into t plus half alpha t square. And this angular velocity can be written as 2 pi n, 2 pi n, 2 pi into frequency. So 2 pi n1 plus 2 pi n2 into time by 2. This linear displacement formula is that, and angular displacement is this. You know, if you want to find number of rotations made by any rotating body in a given time interval, you need to find first angular displacement only. If you find angular displacement, then you can find number of rotations. So, because angular displacement is equal to 2 pi into number of rotations made during the time interval. One rotation, if the body makes one rotation, angular displacement is 2 pi. For n rotations, 2 pi into number of rotations, theta. So using this, you have to find number of rotations. To find number of rotations, you need to find angular displacement. In fact, in the May 3rd exam, they gave a question on this. They gave a fan makes frequency of fan increases from 600 RPM to 1200 RPM in 10 seconds. The number of rotations made by a fan increase from 600 RPM to 1200 RPM in 10 seconds. Find the number of rotations made, he asked. Find the number of rotations made by the fan during this time interval. This problem they asked, that you find it using this only. First find angular displacement. N given here, RPM means not radian per minute. RPM is rotations per minute. This is frequency, not omega. This is one area where students usually do mistake. Omega angular velocity, its unit is radian per second. Theta angular displacement radian. Frequency unit is rotations per second. RPS or RPM. This is frequency, not omega. Be careful while doing this. Now, frequencies are given n1 and 2, 2 pi common I am taking, 2 pi into n1 and 2. But here n1 and 2 are given in rotations per minute. I have to convert into rotations per second. That is 600 by 60 I have to write now. Rotations per minute, 1 minute, 60 seconds by 60 I have to write now. So this will become 600 by 60 means 10. And this final frequency 1200 by 60, 20, no, it will be RPS. So 10 RPS, 20 RPS. N1 10 RPS, N2 20 RPS. Time given as 10 seconds there by 2. So what you will get here, this 13, 20 plus 10, 30 into 10, 300, 2 cancel. 300 pi radians. This is the angular displacement of that fan in this 10 seconds. But is asking number of rotations. Now using this, you have to find number of rotations made by fan during the 10 seconds. This theta 300 pi given is equal to 2 pi into number of rotations. Number of rotations, X I am writing, okay? X I am writing. Then X equal to 150 will get. See, this is given May 3rd exam. Similarly, now, next to linear velocity, angular velocity. Linear velocity V, angular velocity omega. Linear velocity, angular velocity relation. linear velocity, angular velocity relation is V equal to R omega. In vector form, if you write this in vector form, V bar equal to omega bar cross R bar. V bar is omega bar cross R bar in vector form. Linear velocity, angular velocity relation. Next, tangential acceleration, linear tangential acceleration R alpha, where alpha is angular acceleration. Linear acceleration, tangential linear rate of change of magnitude of linear velocity, this AT. Alpha, rate of change of magnitude of angular velocity, omega, rate of change of omega. This in vector form, if you write, if this V bar equal to omega bar cross R bar, V bar equal to omega bar cross R bar, if you differentiate with respect to time, dV bar by dt will get no dV bar by dt. The dV bar by dt only AT bar. Omega, differentiation of omega, d omega bar by dt is alpha bar cross R bar not changing, not time to time. What is changing here? Time to time? Omega, not Horn, position vector of the particle not changing. So AT bar equal to alpha bar cross R bar. This is this linear acceleration, angular acceleration formula in vector form. Next, in linear motion, force will change the linear motion. Force will change the linear velocity, either in magnitude or in direction. Force will change the linear velocity. This force equal to what is force? Rate of change of linear momentum. Force is rate of change of linear momentum. F d by dp bar by dt, F bar. Like that here, in rotatory motion, the state of rotation is changed. The angular velocity changed. State of rotation is changed by torque. Angular momentum is changed by torque. So, corresponding to force here, it is torque in rotatory motion. This torque tau bar is dl bar by dt. What is L? Angular momentum of that rotating system. Torque is rate of change of angular momentum. Okay, now one of the formulae for force, when mass is constant and only velocity of the system is changing, then this dp bar by dt will become ma, mass into acceleration. Like that here, the torque formula is I alpha, where I is moment of inertia, alpha is angular acceleration. Moment of inertia, mass. Observe them. Whatever role mass is playing in linear motion, that role is played here by moment of inertia. Wherever mass comes in the relations in linear motion, their moment of inertia will come in corresponding rotatory motion equations. I, moment of inertia, decides inertia in rotatory motion. Mass decides inertia in linear motion. F is ma, torque equal to I alpha. This another, remember this. Next, one more, linear kinetic energy, half mv square, rotational kinetic energy, half I omega square. Linear, rotational, kinetic energies, half mv square, half I omega square. Next, work done in linear motion, product of force and displacement now. Work done in rotatory motion is product of torque and angular displacement. So like this analogy, linear motion, rotatory motion. Comparing rotatory motion with linear motion, if you learn this chapter, it will be easy for you. In this chapter, students, you remember in this chapter, what you do is you do the NCRT examples, NCRT back exercises and PYQs, practice them around 50 MCQs, practice them in this chapter, very easy to score. See here some relations I gave. V equal to U plus AT model equation. Omega is omega naught plus alpha T. Linear displacement. V square minus U square 2AS model equation in rotatory motion is this. And you need to remember, memorize moment of inertia formulae. Ring moment of inertia with respect to axis through center and perpendicular to the plane, mr square. Disk with respect to axis through center and perpendicular to the plane, mr square by 2. Solid sphere with respect to diameter as axis 2 by 5 mr square. Hollow sphere 2 by 3 mr square. Rod with respect to center and perpendicular to length, ml square by 12. With respect to axis through one edge and perpendicular to length, ml square by 3. The standard moment of inertia formulae, memorize them. Hollow cylinder moment of inertia with respect to its own axis is same as ring moment of inertia, mr square. Solid cylinder moment of inertia with respect to its own axis is same as disk moment of inertia, mr square by 2. So this moment of inertia formulae, you remember, memorize them. And in this chapter, you need to focus on moment of inertia, radius of gyration problems, torque angular acceleration related problems, conservation, angular momentum and conservation of angular momentum questions. Rolling motion, rolling body will have both linear and rotational kinetic energies. Now, rolling body, that rolling motion concepts are to focus. Torque angular acceleration, moment of inertia related questions, and angular momentum and its conservation, rolling motion. This you need to focus. Come on, let us solve some problems. Let us practice. First problem, two spheres of equal masses, one of which is a thin spherical shell, hollow sphere, other is solid sphere. They have same moment of inertia with respect to their diameters. The ratio of their radii is as easy in a formula based. Hollow sphere moment of inertia, solid sphere moment of inertia equal is giving 2 by 3 m r1 square hollow, RH I'm writing hollow, 2 by 3 mRh square is equal to 2 by 5 mRs square. These two equal is giving. They are of equal masses he gave. Same mass, cancel, 2 cancel. Find the ratio of their radii. What is first one? Spherical. Shell means hollow sphere first. Next to RS. So you have to find RH by RS whole square is RS square by 3 by 5. Root 3 by 5. Root 3 is to root 5. Next, a solid cylinder has a mass m, length L and radius R. What is the moment of inertia of this cylinder about one of its generator? Generator is giving generator axis. Generator, you know what is generator for a cylinder? Solid cylinder. This axis is there, now its own axis, axis through center, like this, own axis. Generator axis mean axis passing through surface of cylinder and parallel to its own axis. This is generator axis. He is asking with respect to this generator axis, this solid cylinder, moment of inertia. Now one important theorem is need to apply. Which theorem? Which theorem? Parallel axis theorem. What is parallel axis theorem? Important point is there in parallel axis theorem. Any body, rigid body, moment of inertia, any body moment of inertia is minimum with respect to axis through its CM. Any body moment of inertia is minimum with respect to axis through its CM. And if you take a number of, suppose this is CM, if you take a number of parallel axes passing through various points on this body, I'm taking many parallel axes, all must be parallel, passing through different points. One of them passing through CM also. Out of all these parallel axes, when it is rotating around this line, when it is rotating around this axis, when it is rotating around other, its moment of inertia is minimum with respect to axis through CM. Its moment of inertia is more with respect to any other axis. And its moment of inertia with respect to any other axis is moment of inertia with respect to axis through CM plus this rigid body mass M into distance between those two parallel axes, axis through CM, another axis. Now we are taking distance between them, A I'm taking. This is parallel axis theorem. We need to apply this. Here, this is CM. And this one axis is axis through CM. With respect to this one axis, solid cylinder moment of inertia is mr square by 12. mr square by 2. Solid cylinder moment of inertia with respect to its own axis is same as disk moment of inertia. Na? mr square by 2. So I equal to mr square by 2 plus m into. What is the distance between this generator axis and this axis through CM? Between these two parallel axes, what is the distance? R only, na? Radius of this cylinder, no? So this is r square, mr square by 2 plus mr square, 3 by 2 mr square. Three by 2 mr square. So I'm moving to next problem. Which of the following are correct expressions for torque acting on a body? Torque acting on a body. What is torque formula? Suppose one rigid body is there. This is capable of rotating, arranged so that it is capable of rotating around an axis passing through this point O. At some point P, you are applying a force in order to rotate this. And this point where you are applying force, that point position vector with respect to axis is R bar, force F bar, then torque equal to R bar cross F bar. Torque magnitude of torque is equal to F for sin theta. In vector form, torque is R bar cross F bar. This is torque now. Its formulae, different forms he gave. Which formula are correct? That is asking. First is torque is R bar cross L bar. What is this R bar cross L bar? This is not torque relation. No? Torque is d by dt of R bar cross P bar. What is this R bar cross P bar? You know what is this R bar cross P bar? Angular momentum. Angular momentum L bar is that, and torque is rate of change of angular momentum only, dl bar by dt, not torque. And this L bar only is giving there, R bar cross P bar, right only it is. So second B option right. And now third one, torque is R cross dP bar by dt is giving. Torque is d by dt of R bar cross P bar. This R bar is that position vector, position vector of the point where force applied. That position vector is not changing now here when it is rotating. Position vector not changing time to time. So this R bar I'll write outside. Then this formula will become R bar cross, R bar outside I'm writing. R bar cross dP bar by dt. Correct. Third one is correct. That means actually here product rule you have to apply while differentiating. What you have to do? dr bar by dt cross P bar plus R bar cross dP bar by dt. You have to do like this. No? What is this dr bar by dt? Rate of change of position vector is linear velocity. V bar cross P means M into V bar, no? Linear momentum. Plus R bar cross dP bar by dt. No? Now see here, V bar cross V bar 0. No? So this will be 0. Torque is R cross dP bar by dt. This is right. And torque is I alpha. Just now I told you that is also right. Torque R cross F. This is also right. B, C, D, E. Right. B, C, D, E. C option. One more point I want to discuss with you, dear students. Directions. Directions I want to discuss here. For example, assume one particle is moving on a circle. Particle I am talking circular motion. One particle is moving on a circle. Then this particle linear velocity direction is along tangent. And suppose this is a uniform circular motion, then it will have centripetal acceleration towards center, also called as normal acceleration. It will act towards center. And this particle will have angular velocity. No? This angular velocity direction. What is angular velocity direction? You remember it? Angular velocity direction is perpendicular to the plane of rotation, either inward or outward. Suppose if the particle is moving on circle in anti-clockwise direction, the thumb rule you apply. If it is rotating on circle in anti-clockwise direction, keep these fingers anti-clockwise, thumb outward, that particle angular velocity is along axis outward. Suppose the particle is moving on the circle in clockwise, keep these four fingers clockwise, thumb is pointed inward. Angular velocity direction is inward along axis now in that case. Like that in this circular motion as well as in rotatory motion, angular velocity direction is along axis perpendicular to this plane. It is perpendicular. Remember this angular velocity, linear velocity directions in circular motion, they are perpendicular, circular motion. Angular velocity, centripetal acceleration direction perpendicular. Centripetal acceleration, linear velocity direction also perpendicular. These two perpendicular, no? Centripetal and linear. Directions, practice directions also remember. Okay, I'm moving into next problem. State whether the following statements are true or false. True, true or false. Tell me. First one, the angular acceleration of an object rotating with a constant angular velocity is always zero. When angular velocity is constant, angular acceleration is zero. Correct only, no? Angular acceleration is rate of change of angular velocity. Angular velocity constant means alpha 0. Correct. True only. First one is true. Next, an object can have moment of inertia without energy. An object can have moment of inertia without energy. Yeah. Moment of inertia is an independent property. No? Whether body is at rest to rotating, it doesn't matter. Body will have moment of inertia. It is true only. Third, the radius of gyration of object is a constant quantity. Radius of gyration is a constant. Nay, radius of gyration, moment of inertia, they are not constants. They depend on axis of rotation. So third statement is not correct. False it is. K depends on axis of rotation. Next, a skater spins faster when they pull the arms in. Uh, because moment of inertia decrease. Correct. When spinning, skater is there spinning. If he brings the hands close to his body, moment of inertia of his body decreases. Then angular velocity increases. But angular momentum remains constant. Law of conservation of angular momentum application. So this is correct only. If spins faster, then it brings arms in due to decrease in moment of inertia. Correct only. First statement true, second true, third false, fourth correct. Next. In the absence of torque, the rotational frequency of a body changes from 1 cycle per second to 16 cycle per second. The ratio of the radius of gyration, law of conservation of angular momentum in the absence of torque. That word is there means it is suggesting angular momentum remains constant. In this case, law of conservation of angular momentum, I1 omega 1 equal to I2 omega 2. You have to apply this. I1 N1 equal to I2 N2. You have to apply this. I1 N1 equal to I2 N2. 2 pi N1, 2 pi N2. I'm writing 2 pi cancel because frequency is given there. Now what is asking? I will do like this. I into N remains constant. Radius of gyration, okay. Moment of inertia, mk square I can write now. Okay, mk square, where k is radius of gyration. M anyhow constant. Then k square inversely proportional to n, k inversely proportional to root n. So k1, k2 ratio root n2 by n1, n2 16, n1 1, 16, 1, 4 is to 1, 4. 4 law of conservation of angular momentum. I want to discuss here one important thing. Okay. Earth spinning around itself with how much time period? 24 hours. 24 hours spinning time period of Earth around its own axis. On law of conservation of angular momentum, based on that, here questions are possible, you know already. If Earth shrinks to half of present radius with mass remaining uh, constant with density remaining constant, like these two conditions they will give, then the new duration of day means time period of Earth rotation. How much? Under this condition, how much? Under this condition. What is first condition? Mass remaining constant, Earth is shrinking to half of the present radius. What is second condition? Density remaining constant, Earth is shrinking to half of present radius. Two conditions. What to do? Here what is happening? Moment of inertia changing. There is no torque, just shrinking, size changing without any external torque there. So angular momentum remains constant. I omega, angular momentum remains constant. I into 2 pi by t remains constant. That indicate I proportional to t proportional to I. What is I? For self-rotation, Earth self-rotation, you should take Earth as a solid sphere, now 2 by 5 mr square you have to write. For Earth revolving around Sun in elliptical orbit, for that rotation, Earth should be taken as a particle. And in that case, moment of inertia of Earth, particle moment of inertia, mr square you have to use. For Earth revolving around the Sun in elliptical orbit. Now, for that, you should take Earth as particle. But for self-rotation like this, you should take Earth as solid sphere and its moment of inertia 2 by 5 mr square you have to use now. Now, in this problem, radius changing. First condition, mass remaining constant he gave. Mass constant. Then I proportional to R square. I proportional to R square. So T proportional to R square. So if radius decreases by 2 times, time period decreases by 4 times. 4 times. That means the time period will become 24 by 4, 6 hours it will become, the new time period. Means if you make calculations, so T2 by T1 is R2 by time waste, na calculations like that. In this manner, you have to analyze and give answer immediately. R2 is R1 by 2, R1 cancel, 1 by 4 you will get. T2 is T1 by 4, 24 by 4. 6 hours is the new duration of day. New duration. Remember, sometimes they'll ask change in the duration, not new duration. Change in the duration of day. 24 minus 6, 18 hours. Sometimes they'll ask percentage change in the duration. Change in the duration, 18 by original duration 24 into 100, 6 3 times, 6 4 times, 4 25 times, 25 into 3, 75%, 75% it is decreasing. Second condition. What is second condition? Earth is shrinking to half of the present radius with density remaining constant, not mass, density gap. Second condition. Okay. How to find now? How to find second condition? Density. I omega, angular momentum remains constant. I into 2 pi by t is constant. T proportional to I. Now, how to write this? See this. How to write? Moment of inertia 2 by 5 mr square. No? 2 by 5 into mass of earth, volume into density, you write 4 by 3 pi r cube into density rho into r square. Now see, density constant, density. See this, density constant. 4 by 3, 2 by 5, pi all are constants. R cube into R square. R power 5 is there. I proportional to R power 5 you have to use. That means T proportional to R power 5. That means T2 by T1 is R2 by R1 whole power 5. That means T2 is T1 into R2 by R1 is 1 by 2. Now R2 R1 by 2. R1 cancel. 1 by 2 power 5. This will get T1 24. 2 power 5 is 32. So this question is important. That's why just I want to remind you, know all this. Next, an object is rolling on a horizontal surface without slipping. If its rotational kinetic energy and translational kinetic energy are equal, what is that object? Ring it is ring. See, when a body is rolling on a surface, this rolling body will have linear kinetic energy as well as rotational kinetic energy. This linear kinetic energy half mv square, this rotational kinetic energy half I omega square. And this is half mv square plus half into moment of inertia can be written as mk square omega v by r, v square by r square. Then this total kinetic energy of rolling body half mv square common if you take 1 plus k square by r square into you will get. This is total kinetic energy of rolling body, sum of linear and rotational. Okay, in this problem, what is giving? Linear kinetic energy, half mv square, and rotational kinetic energy, half I omega square, both are equal, he is giving. So, half mv square is equal to half mk square. I came mk square, I am writing. Omega v by r, v square by r square. V square by r square, half v square all cancelled. K square by r square is 1 you are getting. K square equal to r square you are getting. What is this? Ring moment of inertia when it is rolling with respect to axis through center. Suppose if you take moment of inertia of ring, what is formula? Mr square. Comparing this with mk square, what you will get? R square, K square equal. K square is R square. For a ring, K equal to R. Radius of gyration is equal to radius only for a ring. So this is ring. Ring this is. Next. Next. A uniform solid cylinder of mass 3 kg. This solid cylinder is of mass 3 kg and radius 10 centimeter. Is connected about an axis through center of cylinder to a horizontal spring. Spring this is. The spring constant given 8 Newton per meter. The cylinder is pulled back. This cylinder is pulled back. Then the spring will stretch and then the cylinder is released. When the cylinder rolls without slipping, it is rolling, not slipping. Then what is the speed of this cylinder when it returns to the initial equilibrium position? Here it is there now, initially equilibrium. From here it is pulled back, released. When it comes back to this place, what is this cylinder speed? He is asking. What to do? Law of conservation of energy you have to apply. Suppose this cylinder is pulled back up to this place, it is pulled back so that the spring is stretched by some x, elongation in the spring. Okay. Now see, in this position, here, I am releasing a cylinder, I am releasing it now. At the time, its velocity is 0. So this spring doesn't have any, this cylinder doesn't have any kinetic energy at that time. No kinetic energy for cylinder. It is at rest at the time I release. Spring is stretched. The stretched spring has potential energy of kx square. Now when I release this, the spring cylinder starts moving and cylinder will be gaining kinetic energy. Potential energy in the spring will be decreasing. And finally, when the cylinder comes back to this initial place, spring will be in the normal condition now. Then spring doesn't have potential energy. So in the final condition, spring doesn't have any potential energy. Only this rolling ring will have energy. That energy, half mv square. Rolling, it is rolling, not sliding, rolling. It will have both linear and rotational kinetic energy. Just now shown total of those two, half mv square into 1 plus k square by r square. Using this, we were to find. That is, what is this k square by r square? For this cylinder, this cylinder, solid cylinder. For solid cylinder, moment of inertia, same as disk moment of inertia, mr square by 2. If you compare this with mk square, in place of k square in the original formula, r square by 2 is there. That implies k square by r square is 1 by 2. For solid cylinder, k square by r square 1 by 2. For disk also, k square by r square 1 by 2. So half of cancel. K 8 given. SI units only na Newton per meter 8. X substitute x 1 meter he gave. See this x 1 meter. It is stretched by 1 meter. 1 square 1. Half of cancel. Mass of the cylinder 3 given. We were to find. into 1 plus k square by r square is 1 by 2. Simplify this. 3 by 2, 16 by 9. V square is 16 by 9. You are getting V 4 by 3. 4 by 3, 1.33. Okay, next problem. Assertion reason. In this chapter, assertion reason match the following to practice that. Means body, moment of inertia, formula, one column, match this type. Assertion. When no external torque is applied and moment of inertia of a rotating body changes, then its angular momentum remains conserved, but kinetic energy changes. Correct it is. When external torque is zero, angular momentum of the rotating system with respect to an axis remains constant. If you change, what is L I omega? No? If you change moment of inertia, accordingly, omega changes. If you increase omega by n times, if you increase I by 1 times, n times, omega decrease by n times. If you decrease I by n times, omega increase by n times. So that I omega remains constant in the absence of torque. So that is correct. No external torque is applied, moment of inertia changes, but the angular momentum remains conserved. Its kinetic energy change. Kinetic energy changes. Na? What is rotational kinetic energy? Kinetic energy and angular momentum relation L square by 2I. Kinetic energy of rotation is L square by 2I. In this concept, L constant, I changing. So rotational kinetic energy changes. Omega changes, I changes, rotational kinetic energy changes, they all change. L doesn't change, angular momentum. Correct, that's assertion correct. Reason, angular momentum doesn't change, does not depend on moment of inertia. This is wrong. Angular momentum depends on moment of inertia. Is giving, doesn't depend on moment of inertia. That is wrong now. So what is answer? Assertion correct, reason right, reason wrong. Assertion correct, reason wrong. Where it is? That is answer. A is correct, but R is not correct. Next, see that a thin rod of length L is suspended from one end and rotates with n revolutions per second. What will be the rotational kinetic energy of the rod? Thin rod, rotational kinetic energy of rod, half I omega square. Here the rod is suspended from one end. Means the rod is hanged from one end and it is made to rotate with respect to axis through one edge. With respect to axis through one edge, rod moment of inertia ml square by 3, and he gave frequency, number of revolutions per second, omega 2 pi n, you write 4 pi square n square. This is answer. 2 by 3, third option. See, one more I want to tell you, rod coming now. So one more I want to tell. Suppose there is a rod. One edge of rod is fixed in this wall. Okay. Here one string is there, string. Other edge tied to a string. If the string is cut, then this rod will like this fall. It will rotate now like this. Then at the instant you cut the string, what is the initial angular acceleration of this rod? They may ask. Why this rod will fall like this without remaining horizontal even after you cut this? Why it will turn like this? Due to gravity that will act from center now. This gravity is creating turning effect, torque. So what you have to do? Torque equal to I alpha, you have to apply. Torque is force into perpendicular distance from axis. Na? This perpendicular distance from axis to line of action of force is L by 2. Na? So mg force, L by 2 perpendicular distance. So this is torque. I what you have to substitute? This rod is turning, rotating around axis through edge. So ml square by 3 you have to write. Then mm cancel, you will get alpha L 3 6g by L, like that you will get. Alpha you can find. This type also they can. Important questions. Next, the radius of gyration of a rod of length L and mass m about axis perpendicular to length and passing through a distance L by 3 from one end. So you take a rod, take one uniform rod. What is asking? This one edge you take one edge because from one end is giving. This rod length is L. From one edge, there is a point at a distance L by 3 from one edge. When this rod is rotating around axis through this point, what is its radius of gyration is asking. I know the moment of inertia, radius of gyration of rod with respect to axis passing through its center and perpendicular to length now with respect to this. This is Cm. With respect to Cm, I know na radius of gyration, Kc it is. I'm taking Kc. I know na this. So using parallaxis theorem, I can find. But to apply parallaxis theorem, I should know the distance of this particular axis from Cm, not from edge. This distance, that is A. So what is this distance? Half of the rod length. From L by 2, I have to substitute L by 3. Then A I will get. How much I will get? 3L minus 2L L by 6. So this A value L by 6. Now if IC is moment of inertia of rod with respect to Cm, I is moment of inertia with respect to this point, then I must be equal to IC plus MA square. I am writing as MK square. IC MKC square plus MA square. M cancel. K square is KC square plus A square. K square is KC square plus A square. K square is KC square plus A square. What is KC? KC. What is IC? ML square by 12. You compare this with MKC square. KC square is L square by 12 plus A L by 6. L square by 36. L by 6 whole square I have to do. Na? Find from this. Find. Next, I want to discuss with you one question. Just I want to discuss. Suppose this is a solid cylinder. One thread is wound around this, and the free end of thread carries a body of mass M. This solid cylinder mass capital M. Its radius is capital R. This is given. When this small m block is released, it will move down now. What is the acceleration of this block? If it is asked, what you do is the tension connected bodies concepts you have to apply. Free body diagram. Tension in the string will act up on the block. Mg will act down. And tension in the string only acts tangentially on the disk surface and responsible for disk rotation. So disk is making cylinder, I told you. Okay, cylinder. The cylinder is making rotatory motion. That rotatory motion, cylinder making. For rotatory motion, what is the relation? Net torque equal to I alpha to apply. Torque is force into perpendicular distance. Force is tension only. Perpendicular distance is R. T into R. I capital M na this mass, cylinder mass into R square by 2. Solid cylinder moment of inertia into alpha. Alpha A by R I am writing. A equal to R alpha, from that I am writing. Next, for block you apply. Block is in linear motion. Linear motion F equal to net force is MA. Net force is mg minus T. This is small m here. That is capital M. Now here one R here cancel, this R also cancel, you will get T equal to capital M into A by 2. That is substitute here. Bring here mg equal to A into this, you bring here M by 2 plus M. Then you can find A. This is also important model. That's why I wanted to discuss with you. Okay, all the best students in this chapter. NCRT back exercise, NCRT examples, PYQs, you practice them. These areas you focus. All the best. May the Almighty bless you all.